Hello everybody, I'm Dr. Sergey Sarkisov. I want to talk about trigonometry. I want to introduce us to trigonometry. And the subject itself is really, what is it, right? So geometry, right, the study of shapes, sizes, positions, right, figures, whatever, right? Well, trigonometry is, I think, a specialization of geometry to study specifically angles and side lengths and the ratios of all those with triangles, right? Trigonometry, triangles. So that's what I think and what I tell my students when I consider what is trigonometry. And so there are some trigonometric functions. Basically, each of those 6 trigonometric functions actually we'll look into is a definition of a ratio of 2 sides to each other in a right triangle. Is initially how we will define it. So anyway, let me go ahead and write the topic for today is indeed trigonometry. Trigonometry. And it's just an introduction, okay? So I want to give us an introduction, but again, a little summary of a lot of the basics that you will be using, and actually that will help you maybe to summarize just what you have already learned in some of the introductory classes in trigonometry, or remember some things and concepts. So anyway, trigonometry. Well, first of all, let's start with the geometric ideas of, okay, there's a point, right? What is a point? Well, it's a 0-dimensional object that basically just tells you the position of something, right? Like there it is. And you don't even have size of that point. Theoretically, there's no size. So if I draw a bigger little point, a bigger point, a smaller point with a marker, really it's the same thing, theoretically speaking, okay? So now, there's a point now, we can get from that point, what if I have 2 points? Well, I get a line, right? That's when you have 2 points. And you have something going on through them. So basically infinitely many points, really. A one-dimensional, so this is now another dimension, a one-dimensional, 0-dimensional, one-dimensional object where a lot of points in the same direction, okay? And so now we can get a ray, right? We get a ray. What is a ray? It's when you have a point and a line going in that one direction only. Okay, so all the points going in one direction from an original initial point, okay? And that's a ray. And what is a line segment? We'll just call it segment. Okay? That is when you have basically a line that stops between one point and another, connects 2 points, but it's only all the points linearly between 2 points. Okay? And these are some ideas. Now, like, what is an angle, right? Well, if you have a vertex, an angle, you need a point and 2 rays coming from it. So angle will be, here's a point, here's a ray, here's another ray, and that angle is that little thing between the 2 rays, okay? This is an angle, actually. This is called a vertex right here. And these are rays. Okay, vertex of the angle, that little point, okay, from which the rays are originating, okay? Now, there's an angle measure. What is an angle measure? Angle measure. And there's, of course, length measure, right? So the length measure is basically using a meter stick, for example, or some unit of measure where you see how long something is, okay, how long that line segment is. And then the angle measure, okay, that actually is somewhat artificial initially, right? Like this is actually like what is angle measure, how big an angle is, right? But it has to do with this idea, Babylonians a long time ago actually used this 360. This is a very long time ago, 360 degrees in a full circle, as in 365, think about it, 365 days in a year, in a calendar's year, right? So the number 360 is a nicer number. It's divisible by 10, it's divisible by a lot of 2s and 3s, okay? So it's divisible by a lot of factors, actually. What is it? 36 is 6625, so that's, what is it? Or there are different ways to say it, but it's 10 times 36, 6 squared times 10, 222,335. It will have 4 times 3, 3, so 4 times, and then 3 times 2, 4 times 3 times 2, 24 factors if I'm not mistaken, okay, some kind of trick that I'm using here. Anyway, so a big number has a lot of factors. Let's go on with angle measure. It's what it is a ratio of how much of a circle something is. So in other words, we have this 360 degrees. Okay, that's just kind of a definition. The whole circle is 360 degrees. And so angle measure is how much of 360 degrees do we have, right? And so that's the idea. That's what I would like us to understand it as. For example, if I have a quarter of a circle, so quarter of a circle, circle is that right angle, okay? Let me show you what I mean by that. 90 degrees, because it's equal to 1/4 of 360 degrees, right? And that actually is this right here. If you just do that, okay, and that angle there, right there, between this and this angle here, and then right there, that's a 90-degree angle. For example, we can do 45 degrees, half of that one, right? Or you can do 180 degrees, okay? That's straight angle. Okay, and so angles also have a lot of properties and names. There's the acute angle, okay? The obtuse angle, the right angle between those, and then the straight angle, even the reflex angles, the bigger angles in the 180 degrees, okay? So those are angles, and when we have angles and we have vertices, we have 3 points. This is when trigonometry begins to originate, or at least a shape that we have more, we have two-dimensional, kind of in a planar shape. And we have, if we have 3 points, we have a triangle, right? And so this is a triangle, 3 points tri, right? Latin, tri, tri for 3, right? So we have, let's say, A here, vertex, B, vertex here, C, vertex here. Then usually you would denote the side lengths, okay? Basically side angle, segment, and you have side length for the measure. So angle measure and side and length measure is the length is the side measure, okay? So the segment measure. So anyway, we have length A here, length B here, and segment AB has length C because they're opposite. Little c across the angle C. These are angles actually. Angle C, angle A, so little a there for the side length there, and angle B has little b across from it. Okay, so this is a triangle actually. It's a big shape, triangle, and because look, you have trigonometry. Triangle, 3, right? Okay, 3 angles, 3 sides. All right, so now what I'm going to do is, instead of going more and more geometric on this, and giving you more definitions and see what an obtuse triangle is, similar triangles, right triangles, I'll take a right triangle. At least you need to know that. So I'll skip a little bit of that geometry stuff. But what is a right triangle? It's one that has one of these 90-degree measures. So let's take one of them. Okay, so let me do that. Let's take a right triangle. Right triangle. Okay, let's go. So we have a right triangle. Now you see, I'm going to have one of this right here. I'm going to have a 90 degrees right here. Right here, 90 degrees. I'm going to put it denoted both ways. This is when you have a little box, like a little square for the angle, that means 90 degrees. The perpendicular, just right to that right here. Okay. So this. 1 second. Put a little meter here. So. And there's my right triangle. And let me call this, let's say, A, B, C. You usually go kind of either counterclockwise or clockwise when denoting the kind of the alphabetical order of the vertices of a triangle or any shape. On the side note, let me show you the side note is this. I'm going to erase this in a moment. But you think, well, what about any shape? What about a pentagon? What is a pentagon? It's I'll erase this soon, but like pentagon is a 5-sided or 5-vertex figure. So 1, 2, 3, 4, 5. Let's make some kind of random pentagon. In other words, here are 5 sides connected, 5 vertices connected by 5 sides. That's a pentagon. Now you think, well, why do we only study the shape of a triangle? You know what? We can make the pentagon out of triangles. For example, let me divide it in a way like this. Here's a triangle. So you see that 3 triangles make up this pentagon. You could have done another way too, divided there and there, for example. So draw some diagonals, and any shape, okay, any shape that's any polygon can be definitely made of a bunch of triangles. Okay? Interesting, right? So if we know triangles, we know a lot of shapes. Okay. I would say there's the linear kind of the shape, the kind of the rectangular shape where you have everything made of straight edges. Okay, polygons basically. And there are also the circular shapes, the curvatures coming into that place where you have pi, that number pi, that number, what is it, trigonometric and geometric number, where you will then, the circular number where you talk about the, actually, it's a big number for when you talk about a circle and how many pi radians actually are, or the same thing as 180 degrees. But we'll talk about that later. Okay, so Pentagon, and so this is a shape made of triangles. I was going to say made up of triangles. Okay, so just so you know that this is not, triangle's a big shape. Even a pentagon is made up of these triangles. Okay, so even pentagon is made up of these triangles. So now look, take this triangle, all right? That's the blue one. Let's denote this angle actually with the measure theta, the Greek letter theta. Okay. Why not? It's like a little circle with a little squiggle through it. Okay, so we're going to do something here. So I'm going to erase this, and I'm just going to make some definitions of some trigonometric functions. Okay, there's sine, S-I-N-E. Okay, what is sine? And what is cosine? There's that one too. We just make up these terms and let them equal to something. These are just definitions. Okay, and you may wonder, why do we do that? Why make things more complicated for ourselves? Why didn't create new material? Eventually, not really visible in this class, but eventually you will be able to simplify a lot of your work knowing this trigonometry and using these trigonometric functions. Okay? And just as a heads up, when you use law of sines, when you're solving triangles, when you're doing law of cosines, or finding, for example, like how tall the ceiling will be if you have at an angle of 47 degrees, a little plank, or the roof being, whatever long, like let's say 10 meters long. So, you can do a lot of stuff with geometry, or when you later go on to polar coordinates or a complex number theory, where you will even do Morph's theorem. Okay, we're not doing that today, but you can do a lot of that. Trigonometry can help a lot with that, where nothing else really can at that point. And you have, or unless you just come back to the basics of defining and inventing trigonometry all over for yourself and then doing it. Okay, so basically, what is trigonometry? It's really just ratios of sides in a right triangle. Okay, that's kind of how we're going to start it up. Look at this. So there's sine, cosine. I'm going to give you 6 trigonometric function names. Sine, cosine. There's tangent, and I'll explain what these are in a moment. There's cotangent. Okay, cotangent. There is secant. Okay, and there's cosecant. Okay, cosecant. And so what is sine? It's written as, it's a function, so it's of something. You take it of an angle. Or think about it, f of x. You don't just say f, right? You say f of x, the function of an input, of the domain element, right? So let's say sine, S-I-N usually written as that, and then of theta. You can put parentheses around it all you want, right? A lot of times I would do that actually, but let me just kind of simplify this with, remember this is the same thing as sine of theta. So it's not like sine O or sino. Okay, it's not that. It's sine of theta, of this. If we put an x, it's not since, it's sine of x. Okay, so cosine is COS, and then of the theta. Tangent, TAN, of the theta. Cotangent, COT. These are just the 3 letters that denote the same thing as cotangent, but COT. Secant, SEC, of theta. And then cosecant, CSC, of theta, okay? And what these equal to, right? What these equal to? By definition, okay? It's just definitions. It's not because I'm creating or making or solving. It's not because I solved any problem and derived that, okay? Sine of theta. Well, let me denote these sides as, maybe this is kind of the horizontal. A lot of times we say x. If it's a rectangular coordinate system, this would be the x value, and this would be the y, the vertical, right? The y. We can also call this adjacent side. Okay, adjacent. Right? Because you have adjacent to the angle, touching, not the hypotenuse, so it's the one that's smaller than hypotenuse. Let's call this r, or the hypotenuse. And this is just notations we want to use, okay? So hypotenuse. Now r will be the length of AB, x or adjacent will be the length of AC, and BC has length y, or also called opposite side, right? It's side opposite the angle theta. Okay? So if the angle theta was here, this would be opposite, this would be adjacent, and this would still be hypotenuse, okay? Hypotenuse of the right triangle does not change. So sine actually is, by definition, ready? Like you have to know this. If you want to know trigonometry, at least you have to know what sine is, okay? Sine is defined as opposite over hypotenuse. Opposite over hypotenuse. So let's write it. I'm going to write OPP, I'm going to abbreviate it over hypotenuse. And that's what it is. That's y over r, right? In our the notion of these letters with side lengths. Okay? Y over r. Cosine. Well, very similarly, but it's adjacent over hypotenuse. Adjacent over hypotenuse. Okay? So let's say ADJ. Abbreviate that over HYP. That's going to be the x over r, right? And then tangent is going to be opposite, by definition, opposite over adjacent. Okay? That's going to be y over x. What about cotangent? Well, if you know a little bit, you'd follow with saying, oh, well, it's adjacent over opposite. Actually, it's the reciprocal of the tangent, but it's not because of that. It's actually later we'll just see that's what it is. But the cotangent is defined as the adjacent over the opposite. Adjacent over opposite. Okay? And that's going to be the x over y. You see, it's a flip, really, a reciprocal of y over x. Secant is going to be kind of a flip of the cosine. Okay? And that's going to be hypotenuse over adjacent. And that's by definition hypotenuse over adjacent, and that's going to be the r over the x. And finally, cosecant is defined as, this one right here, as hypotenuse over opposite. So hypotenuse over opposite, okay? And that's going to be what r over y, right? Okay. It's just kind of these are definitions. And you may wonder, well, what's the point of all this? Well, that takes time. It's time to see. For example, if you're learning music, and you're learning the key structure, and you're learning the notes, and you're playing piano maybe. Well, you're not playing piano right away. You're just basically, C, what is C sharp, what is C, D, E, right? You're clicking those keys, and you're learning that because you can't compose something easily by telling me, hey, look, for 5 seconds, okay, in 5 seconds, you're going to start by clicking the 35th key from the left on the piano keyboard. And then wait a second and click the 38th, or press it down on 38th. If you do that, right, that's not going to be possible, highly impossible to follow, when you, especially composing. What is that? Composing a masterpiece, whatever, right? In music. So similarly, you don't want to keep on saying adjacent over hypotenuse, I need to use that. You just want to say cosine theta and move on. That's really simplifies a lot of things and gives you that strength, that tool to do a lot. Okay, trigonometry is that. So now look at this. What we're going to do now is we're going to try to remember that. Okay? One more thing you can do is you can kind of think about the unit. There's a unit circle idea, and I want to introduce that to us just quickly. Okay, we're going to look back at that, of course, later. But so this is the right triangle, kind of trigonometry. Right triangle. And just as a heads up, we will talk about the unit circle. Now look, the unit circle, let me just use green for this for a moment. So green will be a unit circle. What is a unit circle? Well, a circle is all points, this is a locus of points, equidistant from a center point, from a point called the center. So there's a center, okay? And then there's a unit, which means it's a 1, okay? And it's all the points one away from, you see that one away from that center point. So one away from that center point. Okay? It's like that. And then look, what you can do is, you can draw a rectangular coordinate system with the x-axis, the y-axis. Okay? And place it like that on the origin, the center point. Okay? Now you have that unit circle that you consider in geometry and in trigonometry, where now let's say we have some angle, any angle. It can be like this, look. 90 degrees, 180, 270, 360, 450. And let's say maybe, why not do, let's say, what is it, 450, and then it's going to be, what is it, 450, 540. Let's do 510 degrees. So maybe I do 510 degrees, okay? So 510 degrees, okay? That's possible. Why limit ourselves to just 0 to 90? Or 0 to 180, right? Or 0 to 360. So we do a 510 degrees, and there is some kind of angle. Go around. By the way, positive angle is when you go counterclockwise, okay? And you start with this, always this is initial side when you talk about this rectangular coordinate system trigonometry. And when you end up here, that's the terminal ray, that's the initial ray, of course, the x-axis, right? And so that's the y-axis. 5 to 10 degrees, and then guess what? If you want to do a trigonometric function of this angle, like theta, of an angle theta, consider this point here, okay? And you would say, hey, look, this is my x, and this is my y. And similar, the same x is y and y is here, okay? And then, you know, this is unit circle, so the r is equal to 1. So actually, my sine, based on this, right, my sine will be kind of the y over the r, which is just 1, right? This is going to be x, because x over 1. This is going to be y over x, the same thing. You still use the same y and x, it's just r is 1. This is going to be y over x. X over y, sorry. This is going to be r, which is 1 over x, and this is going to be 1 over, right, 1 over y. So if you see this, we're talking about the unit circle, and this is going to work for almost any angle. Basically, for any angle, in any, like, that's how you would set it up in the rectangular coordinate system, okay? And whenever you have the x, y, you basically have the cosine and the sine. And then you work from there to get anything else, okay? All right, so again, we're going to talk about that, you know, later. That's just a little heads up, introductory. So let me show you what I would call common angles. Okay, let me talk about common angles and common triangles in that sense. So let's look at the 30, 60, 90 degree case. 30, 60, 90 degree triangle. What is that? First of all, let me show you something really neat. And also, there's a lot of geometry, and even trigonometry kind of touches upon this, with two parallel lines, and when you have a transversal cutting them, you have pairs of angles, and you call them things like alternate exterior angles, or corresponding angles, or vertex angles, okay? Or, vertical angles. But so, what I'm going to do is quickly, let's do this here, before I do the 30, 60, 90, let me show you something really, really cool. I think you'll like this. So, I'll leave it there, but look, here's a parallel line, okay? And here's another parallel line. So here is a pair of parallel lines. What are parallel lines? It's lines that I could have done these definitions here, but I'm skipping a little bit of that. So parallel lines is two lines that go on and on and on. Okay, it's in two dimensions really at this point, and they never intersect. Okay, never intersect. Just go in the same direction. So basically, the same direction, so they'll never touch, right? And let's draw a point here. Okay, a point here and a point here. For example, actually, let's say I already had a triangle. Here it is, okay? Let me show you how I would kind of set it up as. So I would say, look, I have a triangle, and I'm going to place it like this to make it look kind of neat. I'm going to place the base on a line, extend a line, okay? And then I'm going to draw, there's a postulate in geometry that says you can only draw one parallel line through a point, not on that line. So a parallel line to this line here at the bottom, we can only draw one such. That's a postulate. And basically, you just have to assume it. We can't prove that. Take it for assumption, okay? At least a lot of people say that you cannot prove that. Okay? So it's a very debatable topic there. But what happens is this. Look, I have parallel lines, and then you can draw what? You can draw, let's say, this angle alpha. Also Greek letter. This angle beta, and this angle, let's call it gamma. Okay. Now, this angle alpha and this angle. What is this? This one and that one. This alpha and this one. They are called alternate interior. They're interior and alternate angles, and actually they're going to be equal in measure. This is also alpha. And this one, this beta, well, guess what? This is going to be beta as well because of alternate interior. And what happens is we know, kind of remember, this is right here, alpha plus gamma plus beta, right? Right here is what? That's half of a circle. And what do I talk about an angle measure of a half of a circle? It's half of 360 degrees. It's going to be 180 degrees. And guess what we have just proven? Alpha plus beta plus gamma is 180 degrees. Whether it's this way or this way. The sum of the angles in a triangle is always 180 degrees. Okay? When a set of angles adds up to 180, we call it supplementary. When the set of angles adds up to 90 degrees, we call it complementary. So this is going to be a supplementary trio of angles. Okay? And in other words, angles in any triangle, sum up to 180 degrees. That's pretty cool to know, right? So when you see, the reason I came to that is because you see 30, 60, 90. What I mean by that is we're taking a right triangle. That's going to be 30 degrees, 60 degrees, 90 degrees, like that. Okay. 109 degrees. Let's call this 30. And let's call this 60 here. Now, what's interesting is, what if I doubled this triangle? In other words, we didn't discuss this yet, but what is an equilateral triangle? What if I had initially even drawn an equilateral triangle? It's when all angles are the same and all sides are the same. And this is actually when all angles are, what's 180 divided by 3? 60 degrees. Now, if this is 30, this is going to be another 30 to make it 60. You see, this is an equilateral triangle, right? And so the one 30, 60, 90, that's only half of that equilateral triangle. So let's say the lengths were, let's remember how we talked about r being 1. Let's say this hypotenuse is 1. R is 1. And then maybe, oh, this is also going to be 1, and this whole thing is going to be 1, right? Because this is, again, all sides turn out to be the same. Why would it be any different? By the argument of symmetry, if this is 60, and that's 60, why would this or this or that be any bigger than any of the other ones, right? They shouldn't be. All the angles are the same, so should all the sides be. Opposite 60 and opposite 60, that one. It's all the same. It's a shape that's very symmetric. And so, 1. Now look, you see this triangle on the top and the bottom there, the triangles there, they're basically the same ones. They're congruent. We didn't talk about that also, that concept of congruence, but congruent triangles. Right? They're basically the same triangles in the side lengths and the angles there. Same shape, everything. Just kind of flipped, right? So this length is equal to that length. And guess what? What's half of the 1? This is a half and this is a half, right? And of course, if that's a half and that's a 1, right? This is actually going to turn out to be this, let's call this y, right? Y is 1/2, this r is 1. This is going to be, let's call this side x, okay? We know the Pythagorean Theorem. Now, I'll prove the Pythagorean Theorem for us also. And then we'll come back to this x. 1 second. Very important to prove the Pythagorean Theorem. Pythagorean Theorem goes like this. Okay. I have a proof of it that I'm ready to give us. 1 second. So it's only one of many, many proofs. Pythagorean Theorem. Okay. So Pythagorean Theorem is pretty cool, and that's what's going to help us find that x, that other side. Okay? Because we have a 1 and 1/2, and what's that side? It's going to actually have to be specifically something. We'll see. And there's a reason I'm doing these sides like that. Okay. So Pythagorean Theorem, ready? Let's see. Let me draw a triangle, okay, like that, and call this maybe a right triangle. I like right triangles, right? Call this A, call this B length, and this is maybe length C. What I'm going to do is I'm going to take that right triangle, flip it 90 degrees, and bring it over here. Okay. So here it is with that's now my A, my B, my C, right? Right triangle. I'm going to take the same one, again, 90 degrees this way and put it down. And you have this A, this B, this C, this is C, this is B, this is A. Okay, this is the right triangle there. And then one more time, and guess what? It's actually connect with this one. Yeah, connect with this one. It's kind of cool, right? Connects. And so this is now another right angle. This is my A, my B, and my C. And you may wonder, well, what about all these other angles? Well, look, if this was an angle, let's say alpha, and this is my angle beta, guess what? Alpha plus beta plus 90 is what? 180. This is also beta. Remember, this is going to be beta, and this is going to be alpha, and this is going to be beta, and this is going to be alpha, because we took the same triangle, right, every time. Beta and alpha. And what happens is, look, if this is alpha plus beta plus 90 is 180, and alpha plus beta plus what is 180, because this is basically a line, right? I rotated it specifically to make this a line. So this is 90 degrees also, right? To make this alpha plus 90 plus beta, alpha plus 90 plus beta. They're both 180 degrees. 180 degrees. Some right triangle, some of the angles in a triangle, 180. So basically, the straight angle, 180. So pretty cool, right? That we have this is a 90 degree, and similarly, this will be 90, this will be 90, this will be 90. We have a square inside. C, 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 right angle, right angle, right angle, right angle. Really cool. Let's find the area of everything. Area is equal to, what's A plus B? That's the length of the side, the big square. This is a big square, right? That's the length, A plus B. So let me do A plus B times A plus B, right, everyone? That's how you find the area. Basically the length times the width, or just side square, in in a square. And this is going to be, if you do the FOIL method correctly, first term's a squared, outer terms ab, inner terms ba, so that adds up to abba, that's 2ab, right? And then finally, plus b squared, the last terms. That's going to be my area of the triangle. Guess what? I have this whole big square. But the other thing you can do is you can say, hey, look, the area of that square, okay, is actually made up of these 4 triangles and the area of the little one. The little one, yeah, for sure, it's c squared, right? And what about the 4 triangles? Well, it's half of AB, right? Half of base times height. And that's because actually this triangle, if you add another one to it, like that, it's going to be AB, it's going to be the rectangle. That's why it's half of that rectangle. Every triangle will have base times height because it's half of the rectangle that surrounds it. Okay? So it's going to be half of AB, and you do that 4 times. This triangle, this one, and this one, right? So I'm trying to get this area, and then this one, this one, this one, and that one. And that's how I'm going to get the c squared plus 1/2 AB, and then times 4, right? Which is going to be c squared plus a 2ab. Right? That's going to be the area of the whole shape itself, whether I color it green or whether I color it red, right? And so guess what? If the area in red, the area red area, and area green area, this, if these are the same, what happens? I mean, they're equal, right? If a squared plus 2ab plus b squared is equal to c squared plus 2ab, the 2ab's will cancel, and you are left with a squared plus b squared on the left side, the 2ab's cancel, is equal to c squared. That is, ladies and gentlemen, the Pythagorean theorem. Okay, so when we basically, I'm saying that for any right triangle, this squared plus this squared, the sum of the legs of the triangle squared, the sum of the squares of the legs of the triangle, is equal to the hypotenuse, the length of the hypotenuse squared. A squared plus b squared is c squared. Okay, whether it's this one, a squared plus b squared is c squared. So coming here, we have x squared, right? This one, plus the 1/2 squared is equal to what? Hypotenuse squared, which is just a 1 here. Okay? All right, and then what do we do? Well, we say x squared plus 1/2, which is squared is 1/4 equals 1. So this is equal to what? 1 minus a fourth equals to 3/4, right? And so x is equal to, take the square root of 3/4, now keep only the positive. Obviously, we're talking about a triangle and its length. Now, we could always go left and right and down and up, right? And that could actually give us a negative. So like if you go left, that's a negative x. Down, that's a negative y, okay? Keep that in mind. But so look, x is equal to now the square root of 3 over the square root of 4, which is 2. Oh, awesome. So we have, this is the root 3 over 2. And you may think, well, what next? Well, here's what's next. What is the sine of 30 degrees? Yeah, you heard me. We can find sine of a specific angle of 30 degrees. How do you do that? Well, here's 30 degrees. I remember, by definition, it is opposite over hypotenuse, always. Okay, in a right triangle like that. Well, opposite is 1/2, right, the length, and the hypotenuse is a 1. That's how you think of what sine is. And so that's a 1/2, right, everyone? Sine of 30 actually is always 1/2. Did I do anything with this triangle? Well, the only specific thing is I made this a 1. But think about it, if I made it a 2, everything was just double here. That would have been a 2, and that would have been a 1 and a 1. Still would have been a 1 over 2. So these are all, if you do similar triangles, if you do the same angles, 30, 60, 90, doesn't matter if it's a 1 or 2 or 3, you can make it all bigger or smaller, the ratio will always be the same, right? And so sine of 30 is always 1/2. What about cosine of 30? Well, that is actually my x, right? X over 1, or adjacent over hypotenuse. And that's going to be our root 3 over 2 over 1, right? Root 3 over 2. And tangent of 30 is going to be, what's tangent of 30, everyone? Go on. That's going to be opposite over adjacent. So 1/2 over root 3 over 2, right? And that's going to be, if you simplify that a little bit, it's actually 1 over root 3, which is exactly top and bottom of root 3. So take away the radical at the bottom, and you get a root 3 over 3. Okay? Pretty cool, right? And then look at this one. What's cotangent of 30? That's going to be x over the 1/2, right? Root 3 over 2 over the 1/2. That's just a root 3. What about secant of 30? That's going to be actually the flip of the cosine, and that's going to be eventually 2 root 3 over 3. Take your time to do that, check that one a little bit. Okay, and cosecant 30 is now equal to, it's going to be, like, let me do it this way. So 1 over a half, right? Hypotenuse over opposite. 1 over 1/2, and that's just a 2. Let me write 1 over a half. That's a 2, okay? And then let me do that with the 60-degree angle. It's pretty cool, right? What about 60 degrees? So if we do sine of 60, similarly, right? And that's going to be equal to now root 3 over 2, because now you're doing at this angle. So you actually do this over 1. Opposite is the x now, okay? Over the 1. So root 3 over 2. What about cosine of 60? That's going to be now adjacent over, over hypotenuse, which is now adjacent as a 1/2 over 1. Now it's cosine of 60 degrees is 1/2. So you see, you have to really understand where the angle is that we're talking about. 60 here, opposite is this. 30 here, opposite is a 1/2. Okay? So cosine 60 is this, and I want to give you everything for 30 degrees and every trigonometric function that we are using for 60 degrees. So I'll quickly do this with tangent of 60 degrees is equal to a root 3, square root 3. Cotangent of 60 is equal to, let's write it here, root 3 over 3. Check these, okay? Everyone check this. Yeah, right now. Pause the video and check this, okay? Cotangent of 60 is root 3 over 3. And then what is a secant of 60 is actually going to be a 2. And cosecant of 60 is going to be 2 root 3 over 3, okay? Pretty cool, right? So check that, and if it's kind of messy there, at least you can probably get it for yourself. These are some things like for trigonometry. These are must-knows. These 30 and 60 degrees, 30 and 60 degrees are common angles. You have to know that. You have to know what to do with that, okay? And let me go on with another common angle triangle. Maybe even easier than this one, actually, for us to derive some of this. Let's use the 45 degree. Let's look into the 45 degree angle, the half of that 90. Okay? And so let me go ahead and erase this, okay? And consider, have a moment, catch up on what we're doing, what we've done so far. Okay? Meanwhile, I'm going to start up with, what's that 45, and a right triangle, so 45, 90, and then 45 is left, right? What's a 45, 45, 90 triangle? Okay. Doing, what is that how is that gonna help us with anything? So let's see. Okay. To do the same thing, we want to find, for example, what if I told you, what's tangent of 45 degrees? Right? Pause the video and think, how would you find tangent of 45 degrees? Well, now let's go to this. So tangent of 45 degrees, let's do this. 45, 45 degrees, 90-degree triangle. That's also sum is 180 degrees. It's a triangle. Okay? It looks like this. Well, looks a little bit more like this if I'm trying to be a bit more neat about it. So kind of a 45 here. By the way, they're both 45 degrees, right? So we have an isosceles triangle. Isosceles. Okay. Right triangle. 90 degrees, 45, 45, okay? Now, if they're isosceles, is this isosceles triangle, 45, 45, what is this length and what is this length? At least they're the same if nothing else. Let's call this length 1 here. Hypotenuse, I like calling it 1. Remember that unit circle idea that we kind of touched upon just lightly for now? Let's call this 1, the length. Let's call this side x. Now, even call it side x. Why not, right? X and y, they're equal to each other. Let's call it just side and side, SS, right? Pythagorean Theorem, let's find the side S. If this is 1, this is going to have to be something. Watch this. S squared, right? Pythagorean Theorem plus S squared is equal to 1 squared. So 2s squared is equal to 1. S squared is equal to 1/2. And S is equal to the square root of 1/2 equals to 1 over the square root of 2. Top and bottom by root 2, and you're going to get root 2 over 2. S is equal to root 2 over 2. S is equal to root 2 over 2. And that was asking us to do this 45-degree angle, the trigonometric functions. Remember I told you, hey, what's tangent of 45 degrees? And if you struggle with that, now we can see, well, it's 45. It's going to be S over S, right? Opposite over adjacent. Remember those definitions. Go back on the video to the definitions of what it meant. Tangent means opposite over adjacent. So root 2 over 2, root 2 over 2 over root 2 over 2, or just s over s. Obviously that's what? That's a 1. And that's what I was asking for. Tangent 45 is always a 1. And let's go up to the sine of 45 degrees. That's going to be what? This is going to be this y over r, right? That's going to be just a root 2 over 2. Cosine also will be root 2 over 2. Okay? Because it's going to be adjacent over the 1, root 2 over 2 over the 1. Cotangent, I'm just going to do this and then you can kind of check for me. It's also a 1 by definitions of adjacent over opposite. This is going to be secant. It's going to be, actually secant will be this 1 over the adjacent, root 2 over 2. And that's going to be 1 over root 2. That's going to be a root 2. And so is cosecant. Cosecant 45 degrees is similarly root 2. Okay? These are very big. And before I give you that, I call it the trigonometry table of common angles and trigonometric functions of those. The 30, 60, the 45 degrees. So this is big, this angle. It's very important. Okay? This angle is very important. We've done this common angle that we're going to basically have to know everything about. So at this point, maybe take a moment. If you want to succeed in a trigonometry setting, class, whatever, you definitely want to know these 12 lines here. You definitely want to know these 6 lines here. You have to memorize them basically. By the midterm of any of those classes in trigonometry, by the exam 1 maybe, you better have it down, like memorized. And a lot of times you just feel it out. Like I don't memorize it to myself. I'm like sine of 30 degrees, half of that equilateral triangle, 1/2 over 1/2. That's one way to do it. Or you can just have it memorized if you are confused about how to derive it quickly. Okay. So, and actually probably I've used this so much that it's just like when I hear sine 30 degrees, I'm just 1/2. Okay. So anyway, let me show you something really interesting. 2 ways. All right. What about the angles 0 degrees and 90 degrees? Kind of a little bit more abstract than this 30, 60, 45. For a triangle, let me show you what I mean by that. Let me take so this has to be a right triangle, right? So here we are with a right triangle. Okay. Here's a right angle, right? So somehow we have a right angle for a right triangle to be there, right? And remember, I used to connect like this, and I get a right triangle. Well, like this one would be my angle here, theta. Well, how do I get 0 degrees? What 0 degrees is this angle so small, right? Basically, really it's non-existent, right? 0. But let's imagine it's so small that it's just basically, here's a point far out from this right angle vertex point, and it's just so thin, like that. That little angle right there, it's about 0 degrees. It's very small, actually. Imagine it being even much smaller, like, right? And this shrinks. This goes to approximately 0, right? If this is 0 degrees. If this is 0 degrees, that's exactly 0. That's approximately 0 degrees. As you can kind of see it. This length here, we're going to call it 1, okay? It's always going to be this, it's going to be 1, the hypotenuse for us now. And what about this length here? Well, that's also about 1, right? It's like you put this line on that one, and they're about the same shape. So this is approximately 1. Okay. So that's 1, and that's 0. Think of it as a 0, 1, 1 triangle. In other words, the 0 degrees, that's a 90-ish degrees right there, right? So it's got a 90, 90, 0. That also adds up to 180. It's an infinitely small, flat triangle. That's the way I want to show you that conceptual understanding of what 0 degrees and 90 degrees could be if you're talking about this right triangle trigonometry. Now, a lot of times you will not see this this demonstration of what 0 degrees, 90 degrees is for this trigonometry, but I want to show you this also. And then we'll do an easier concept of that using the unit circle. First, let me ask you, well, if this is the case, if this is kind of the idea that we're trying to go for here, what is sine of 0 degrees? Well, here's 0 degrees, kind of, right? It's not really, but here's make it smaller and smaller. Make it very small, 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 small. Shrink it to 0 degrees. Okay? Limit. It's kind of a calculus idea, right? Because a calculus actually, which we haven't really studied yet, most of us, is this idea of limits. When something approaches 0, okay? It's a big thing that you start off calculus with is understanding what is a limit. And it's basically approaching, this is actually a very good idea, introduction, a little bit of that. Okay, so anyway, as sine of 0 degrees, it's opposite over hypotenuse, 0 over 1. That's 0, right? So again, that's not exactly concrete, that's not really formal here, but look, kind of 0 over 1. What is cosine of 0? Well, kind of 1 over 1, right? 1. You know what sine of 0 is? 0. And cosine of 0 is always 1. Pretty cool, right? Tangent of 0 is going to be kind of 0 over kind of 1. Okay? Cotangent of 0? Degrees? All right. That's going to be 1 kind of over 0 kind of, right? That's undefined. Can't do that. Can't divide by 0. Okay? What about secant? Secant of 0 degrees. Well, that's going to be hypotenuse over adjacent, 1 over the kind of 1, like kind of similar, approximately 1. So that's actually 1. Kind of like the flip of the cosine, and then sine, you're going to get cosecant, it's going to be 0, it's going to be 1 over 0 now. The 1 over the kind of 0, and that's going to be 1 over 0 equals 2 undefined, right? These are big, okay? So we got everything for 0 degrees. And let's do something with what about 90 degrees? What about sine of 90? What about cosine of 90? Think about this. As I'm writing these, maybe you can get one already. Tangent of 90. Okay? Maybe think about what's the sine of 90 degrees? Cotangent of 90 degrees. Secant of 90 degrees. And cosecant of 90 degrees. Okay? Think about that. What would it really be? Okay, so sine of 90 degrees, let's look at that. That's this one-ish. Okay, kind of. Instead of me drawing another diagram where it's going to be vertically so tall, how about this? If this is 0, this is approximately 90 degrees. They're about parallel lines, really. It's about, really, like if it would be exactly 90, these lines would just be parallel, and just be kind of like, that's not really a triangle, right? Just like a line in itself. So we're approximating with like 89.99999 degrees, or this one like 0.0000 something, right? Very close to 0. So sine of 90, opposite, approximately 1 over 1, right? Hypotenuse. 1 over 1 is a 1. Oh, sine of 90 is a 1. Sine of 90 degrees is 1. Cosine of 90 degrees, that's going to be what? Adjacent over hypotenuse, about approximately 0 over 1. 0 over 1, that's a 0. Tangent of 90, well, that's going to be my opposite over my adjacent, approximately 1, approximately 0. That's undefined. And what about my cotangent of 90? That's a 0 over 1, that's 0. Secant of 90, 1 over 0, right? That's the hypotenuse over the approximately adjacent. Approximately 0, so that's going to be undefined also. Cannot divide by 0. And cosecant of 90 is actually just a 1. Think about why. If you're confused about why this is 1, just like the sine is 1, think about that. Okay? So stop, every time I say kind of stop and think about it, make sure you get it. Okay? This is not something you want to move on from if you don't get it. Okay? Why is this equal to 1? Remember, cosecant, again, is hypotenuse over the opposite. Okay, now, we have here this in blue, 45 degrees, here 0 degrees, here 90 degrees, 30 degrees, and 60 degrees. Let's set up a table for all of these. Okay? Oh, and one more thing before I do, and then we're going to call it class from there, but let me show you really quickly what I meant by 0 and 90 degrees in a unit circle. This is very big too. So, unit circle for 0 degrees and 90 degrees. Okay? It's a little easier. So, here's the unit circle. Okay, let's do that. Here. And you don't always have to draw the whole circle, okay? But so, some kind of circle is kind of like that. Definitely look better than that, but if you drew a better circle. But look, here it is, something like that, right? Now, look, this is 0 degrees, right? And this is 90 degrees. This point. This is 9 degrees here. This is just when you start at 0 degrees. What is my point here? It's 1 comma 0, right? It's again, radius is 1. We call it a unit circle. And this is point 0, x is 0, and y is up 1, right? Remember, cosine is the x, and sine is the y. Remember, x over 1 is the cosine, y over 1 is the sine. So this is my sine of 0, no, cosine, that's my the x value, right? So x value is cosine of 0 degrees. This is my 0, which is sine of 0 degrees. This is 0 here is a cosine of 90 degrees, right? And 1 here is a sine of 90 degrees. And you go on from there with tangent, cotangent, secant, cosecant, and you get exactly the same as we did up here with the artificial making up of a kind of a zero triangle, right? A really squished triangle. Whereas here you actually get the concept more easily. Here's a point 1, 0, here's a point 0, 1. Okay, that would make sense to define the cosine of 0 as 1. Sine of 0 is just a 0, right? The x is a 1, the y is a 0 there, and 90 degrees, that's the other way around, okay? All right, so that's interesting. I kind of get that a little, it's a very small picture here, I think, and just kind of rushed it a little bit, but I want to make sure you get that this is another way to show what we did here, and this is a little bit more, let's say, rough. A rough version of what this would be, okay? So just remember this. Let's go ahead and make our, together, the trigonometry table, as I call it, of common angles and the ratios of them, and we'll call it class for today. So, let's go ahead and erase this part of the board here. Okay. Actually, I just wrote that, but I just erase it all. So remember that if you didn't catch it, I'm going to erase the whole board. And we're going to, and you just take a pause for a moment as I'm erasing and think about what we did. Okay? So, let's see. Here we are. Erase everything. So maybe this is good if you can kind of, without seeing anything, still get it. Okay? So kind of, if most more of you here today, I would say, hey, as a class, let's do this. But I'm just going to do this for us. So kind of, let's see. So trigonometry table. I'm going to call it the trigonometry table. Okay. Trigonometry table. And so, here we go. Do this one set. Okay. What I'm going to do is I'm going to say here is my set of angles. So maybe put a theta here. Angle theta. Okay. And maybe it's this way. And then this way. It's going to be my trigonometric function. Trig function. Kind of the name of it. And it's going to go this way. So here we go with the table. And so already I'm going to start with saying here's a sine. Okay. Here's a cosine. Here's a tangent. Okay. Here's a cotangent. Here is a secant, and we're going to do cosecant here. And again, those have words to them as well. You can write S-I-N-E. You can write cosine, right? Tangent, right? And so let's do this with draw some kind of horizontal lines, just to kind of dividers. Let's do that. Okay. Tangent goes in this row. Here's a row. It's a little matrix of numbers here that we're going to create, right? A little table, right? Secant and cosecant. Now here's the. This is trigonometric function. This is angles. So angle would be, angle theta will be, let's try, and this is just, of course, not really anything there. 1 second. So let's do here 0 degrees. Okay. Right here. And so there's a little box here. Just separate that. And so angle theta will be 0 degrees. Let's try 30 degrees next. That's the one we talked about. It's the next one, larger a little bit. Let's try 45 degrees after that. And remember, we also did 60 degrees initially. 60 degrees. And of course, we ended up with that 90 degrees. Remember that? 90 degrees. So we're talking about 0 here, 30, 45, 60, 90. I want to fill all this in. Ready? Let's do it. So, sine of 30, remember I kept talking about it being 1, half, right? Tangent 45 I asked you, and some of you came up quickly with, that's a 1. We just did sine of 0, remember that's the y, when it's a point 0, 1, 0, right? 1, 0, that's a y and 0, right? And cosine will be a 1 right away, right? Okay. Cosine of 30, that was when we found that little length square root of 3 over 2, right? And it's going to be root 3 over 2 over the 1. Cotangent, it's a flip of the tangent, 1 over 1. Let me just do it kind of all kinds of ways to get all these numbers somehow. All right, 45 degrees, what's sine? Remember we got that to be a root 2 over 2. Okay? Cosine of 60 degrees. It's just like sine of 30 degrees. Think about y. Also 1/2. Okay? Tangent of 0 degrees. That's going to be sine over cosine, turns out. It's that point 1, 0. 0 over 1. Remember the y over the x? That's going to be a 0. Cotangent is going to be undefined. And again, anything I say that you're confused by, make sure you stop the video and think about how you would do that. Okay? Secant of 0, that's going to be the flip of the cosine. The reciprocal of this 1 is a 1. Okay? And cosecant will be undefined. And it's 1 over 0, turns out. 30 degrees. What's tangent? Well, let's do this over that. And it's going to be a what? It's going to be a root 3 over 3. Cotangent is actually just a root 3. Okay, if you remember what we did earlier, you get it. Secant of that's going to be a 2 root 3 over 3. Okay, that's going to be a flip of this. 2 over root 3, and then you get 2 root 3 over 3. That's just going to be a 2 for cosecant. 1 over the sine, turns out. It's going to be the r over the y. R over the y for 30 degrees. And that's going to be the 1 over 1/2 or 2. Okay, now cosine of 45, that's also root 2 over 2. S and S, right? Remember the S's? That was a 1, that's 1. That's going to be a root 2. That's going to be a root 2, the flip of this. Okay, root 2 root 2. 60 degrees, this is going to be now root 3 over 2. And this is going to be a root 3. This is going to be a root 3 over 3. Turns out a cotangent. Okay. Secant of 60 degrees, that's a 2. It's like a cosine flipped, 1 over 1/2. So hypotenuse over adjacent, which is going to be a 1 over a 1/2 for 60 degrees. And this is cosecant is going to be a 2 root 3 over 3. Okay? Yep. Finally, 90 degrees. Well, it's kind of that point 0, 1. Sine is the 1. Cosine is the 0. Tangent is 1 over 0 is undefined. Okay? Cotangent is actually 0 over 1. It's going to be 0, about, right? Secant is going to be what? It's going to be the 1 over the 0 here. That's undefined also. Okay? And then finally, this is going to be a 1. Cosecant of 90 degrees. Think about why I'm getting this one to be a 1. Okay? That's our trigonometry table. Okay? And that's we proved every one of these. We took it somehow into consideration, every one of these values, and somehow kind of got an idea of why that would be the case. So before we move on to our next lesson, make sure you really solidify your understanding of all of these trigonometric functions of the common angles in our trigonometry table. Okay? Thank you so much for joining me. Have a wonderful day.